Okay, so dividing radicals. I'm going to teach it a little differently than I've done in the past. And truth be told, it's going to be a little over your head at first, but just bear with me. So when you're dividing radicals, it's like multiplying radicals. You want to do the factoring at the beginning rather than try to do the math at the end, just because you deal with smaller numbers. So I'm going to show you those strategies. What you look at on number 1 especially is first make sure that the numbers themselves are not perfect squares. For instance, the square root of 49 is a perfect square because when I build that factor tree, it's 7 times 7, which means there would be no remainder, so 7 just comes out. The denominator is 100, which is also a perfect square because 10 times 10, so 10 would come out. And then the last thing you check for whenever you have this is, can you simplify that further, like 7 over 10? Well, nothing goes into 7 and 10, so this is literally your answer. But of course, that's not how easy it's going to be. It's going to be where you have to build the factor tree. So I'm just going to show you how I kind of use that application for multiplication to help you. So for instance, number 2, I could definitely spend time simplifying both and then simplifying later, but we're going to try a different strategy. So for instance, I'm going to build my trees. So 8 is 4, 2, 2, and 2. And then 32 is 8 and 4, which is 4, 2, 2, and 2. And then 2 and 2. Now the hard part about this is you want to kind of keep it organized about which tree is on the numerator and which tree is on the denominator. So you're more or less looking to where you can cancel. That's a silly word, but it's essentially simplifying the radicals where you can cancel the same terms. So for instance, on the numerator, I have 2 or 3 2's that I can essentially cancel. So again, I'm going to try this. I have 3 here, so I'm going to cancel 3 in the denominator as well. So if you notice, I don't have a remainder in the numerator, but I have to simplify somehow, so that's going to simplify to 1. So since essentially nothing left to cancel or no remainder, it's just a 1. Whereas in the denominator, I canceled those 3 2's, but I'm left with a pair of 2's. And normally with a pair of 2's, remember, you bring it out to simplify. So that would be 2 with no remainder. So that would be 1/2. Again, if that did not make sense, let's do it again. So for instance, number 3, 3 can't simplify any further, but we're going to think of that as a branch. And then what's weird about the square root of 16 is 16 is that perfect square. So it has a pair of 4's that comes out with no remainder. So 4 comes out with no remainder. And so this one is a strange one because there wouldn't be no pairs. There's nowhere that I can simplify. So my answer is just the radical of 3 over 4. That one's kind of a strange one. Number 4 is similar to number 1, or not number 1, similar to number 3. 7 technically doesn't simplify past 7, but it does have a perfect square in the denominator, which would be square root of 7, so 7, which comes out because it is a pair of 7's, but it does not necessarily cancel with the numerator because that one was a radical of 7. Again, a little tricky there, but let's talk about what you're really going to see for the next few days. So for instance, number 5, I build my factor tree. So here's 5 and 2 in the numerator. In the denominator, I have 5 and 9, which is 3 and 3. Now, if you notice, the 5's from the numerator and denominator would essentially cancel, but I still have a remainder of 2 in the numerator, so that one stays underneath the radical. And then the denominator would be a pair of 3's, which would come out, but there would be no remainder left. So it's just 3, like that. Again, let's do that again, number 6. So let's build our factor tree. Although the 36 is a perfect square, so that would just essentially factor into 6 and 6, and there would be no remainder. So it's just 6 in the denominator. But 12, like we always do, would be 4 and 3, which would be 2 and 2. That's my pair of 2's with the remainder of 3. But where I have to look carefully is, can you simplify this further by looking at the coefficients? 2 over 6 technically simplifies to 1 over 3, with that remainder of 3 still in the numerator. So it looks like that. If I look at number 7, again, 64 is technically a perfect square. It would be 8 and 8, so it has no remainder, and then it's over square root of 2. And I can't simplify this any further. Tomorrow we're going to talk about how to get rid of the radical that's in the denominator, but for today we're going to leave it. Let's talk about number 8. So again, we build our factor tree. We have 108, which would be 2 and 54. 54 would be 9 and 6, and then 9 would be 3 and 3, 6 would be 3 and 2. And then I look at what 6 would factor out, even though it doesn't have two pairs, but that's the purpose of the dividing, is seeing if we can cancel. So for instance, I can cancel this 3 and this 3, and I can cancel that 2 and that 2. Notice I have nothing left in the denominator. So there's no remainder, there's no factor coming out. So I look at what's left in the numerator. And we have a pair of 3s, which we normally bring out to multiply times 7. So that's 21. And I still have this remainder of 2. There it is. And trust me when I say there is another way I could do this, and I can definitely make a video to show that, but I'm going to try in this way to see if it saves us time later. Let's look at number 9. So for instance, the 5 is just 5, nothing to do there, but then my factor tree for 45 is 5 and 9, which is 3 and 3. So if we look at it, again, we look at what we can cancel, which essentially would be 5 and 5 there. And then I have my pair of 3s, which would be here. When I take out that pair of 3s, there's nothing to multiply, but it's just 3. But then I still had this 3 in the numerator, so oddly enough, this ends up canceling or simplifying to 3 divided by 3, which is just 1. A strange question, but it is that easy. If I look at number 10, I factor the factor tree out, so this would be 5 and 3. This one would be 3 and 9, which would be 3 and 3. Again, I look to see where I can cancel in any pairs. Well, here I can cancel I can cancel some 3s. I do have this pair of 3, so that would be 3, which multiplies times the 3 outside, which is 9 in the denominator. I did have a remainder of 5 in the numerator, so it would be 4 with a remainder of 5, because you don't bring out the 5, and that's it. Number 11, again, I factor my tree out, so this would be 4 and 12. 12 would be 4 and 3, 2 and 2. 4 would be 2 and 2, and then nothing on the denominator. But I do, or I can cancel these 3s, and I have no remainder in the numerator, because whenever I have my 2 pairs of 2s, 2 pairs of 2s is 4. 4 times 10 is 40 over 2, but 40 over 2 simplifies to 20. Like that, no remainders. If I look at number 12, I have 84, which is divisible by 4. 4 goes into 84 21 times. 21 is 7 and 3, and then 4 is 2 and 2. Then 7 I leave alone because you can't, but I do cancel the 7 and the 7 from the factor tree on the numerator. I have this pair of 2s at the top, which multiplies times 3, which is 6, with the remainder of 3, over just 15. But remember, we have to see if I can simplify this further. 6 over 15 simplifies further to 2 over 5, but I still have that radical of 3. And again, if that went over your head, we're going to do it again tomorrow. The only thing I'm going to add tomorrow is what happens if you end up with a radical in the denominator like there was number 7. But we'll talk about that tomorrow.